This is, fortunately for us, this is a kind of a light class. I was just going to go over the final bits of face detection and the AdaBoost algorithm for face detection. From the next class on, we will actually move on to additional topics on representation and such like. But since this was the off week on meta classifiers, and we were introducing a few concepts along the way. While boosting and face detection were the platform, the idea of how you can look at additional principles for how you can trust classifiers, how you can weight instances, and so, etc., things that you can actually carry with you beyond the topic itself. So here's what we've seen so far. We're looking at the problem of, come on, go back. Wait, let me try this. Okay, I'm going to use this, okay? We're looking at the problem of detecting faces and images, and this is what we saw. A typical face, a basic idea, for instance, could have been to represent faces in some mechanism that captured get some notion of what a face looks like, right? And we could get this using, say, the principal eigenface. And this is just for reference. If you had a whole bunch of eigenfaces, then each image can be viewed as the set of weights with which these bases are combined, right? But anyway, when you wanted to detect faces and images, the basic idea we said was you might have a complex image of this kind. You want to find every face in it. So it's not about classifying the image itself. It's about detecting every face in it. And the simplest mechanism to do so was to scan. The most trivial mechanism was to come up with some kind of a typical face. You would typically normalize their picture to some standard size based on the size of your typical face. And you convert it to grayscale because it turns out that there isn't a whole lot to be gained by working with color. Typically, you also standardize, you normalize the color by normalizing the variance of the pixels in the image to 1. And that way skin shades go away, right? And then we said we could just scan using our typical face. And this was a very trivial way of doing it. And the way we would scan, the idea of scanning was to define a match between the typical face and the underlying image, which was just a dot product, right? So this is all from the last class. And we would find you'd get a heat map of this kind. Wherever it peaked, you can expect to see a face. So far, so good. Now, somewhere here, we also noted that even this simple mechanism is going to run into issues when you have scaling problems. And so the solution here was to scale the image so that your typical face was the correct size for the face that you were scanning for. So this particular image, you would have to scale it, you'd have to run it at many different scales to detect every single face in the image. Now your choices are scaling down your typical face or scaling up the image. It turns out that scaling up the image makes a whole lot, or up or down the image makes a whole lot more sense than scaling your eigenface, right? And so we'd go through a scale pyramid, right? Now, the sliding windows and scale space pyramid will yield millions of windows to investigate, particularly for small objects and large images. So now here's the problem. Even this very simple mechanism, right? I'm trying to find faces here, and I'm using a trivial inner product to find the face. How expensive would it be? You're going to have to check every single position, right? And at each position, you're going to have to compute a inner product. And you'd be doing it at many different frames per second, right? What do you think is a good number of frames per second is for an image?
30.
30, sure? So movies typically show it at 24 or 30 frames per second. Your computer games, they're 60. 30 is not enough. The only reason movies can get away with 24 or 25 frames per second is that in the process of capturing the image, they capture image blur. Every individual frame has a little bit of image blur. So you see them in sequence, your brain stitches them into motion. But then if you look at the standard games you play on your computer, I'm sure pretty sure all of you do. If you brought that down to 30 FPS, it would look staccato. For smoothness, you'd actually need 60 FPS. So, once you begin looking at things going that fast, this kind of operation is not going to be feasible, right? So, and then of course, if the objects are small, like the smallest scale of face over there, the number of positions at which you'd have to scan is going to be enormous. And so we have a problem, right? And then you have these additional issues. You might want to deal with position, angle, and so on. Then again, even just using our typical face solution, you'd have to rotate it in every possible way and then scan it. And so you can see how the whole thing blows up, right? So, face detection, as I said, has a long history, and it has always been or used to be a very slow process for the simple reason that you'd have to be scanning the image at many scales. And at each position, if you're performing a feature computation, you have a feature detector. What did we just use? We just used a inner product computation using a typical face, right? And how much compute did that need to compute the value at one point? How much compute would that need? Pardon me?
The size of the face.
The size of the image, right? So if it's n cross n, it's going to be n squared pixels. And every one of those is going to result in a multiplication and an addition. And that's for one position, right? N squared. And then the number of positions at which you scan, and the number of scales at which you scan, and then the n is going to change. So you can see this blows up, right? And this is just one feature. If I'm computing a whole bunch of features to perform this face detection, then it's going to scale up with the number of features. And the number of features we typically need is going to be in the order of thousands, right? And so, first, here's a problem. What happened?
The camera is.
Why is the camera off?
It's focused on the broad. Instead of exposed.
Okay, you got more time for this particular poll. Thanks to Adnan. Thank you, Adnan. To make up. So to make up for this poll, all subsequent polls are going to be only 10 seconds long. We must save time. You're trying to display straight from my laptop? Why? That's not going to work. Desktop. Yeah. Nothing's showing. Okay. Can I take this off? I'm going to show the desktop, not the laptop. Because the desktop has the. Oh no?
Now it should, I think.
Right?
But now it's showing this.
That's because it's showing. Okay, can you see it on Zoom? Perfect. Okay, let's continue, right? So somebody on Zoom, can you tell me all the true statements? What are the true statements? We have a few people on Zoom. Okay, the folks on Zoom. Pardon me?
Second one only.
The second one, right? You don't need, like I said, you don't really want to be using full color images. If you just look at the variety of skin shades in just this room, there's so much that when you begin looking at color, it's not going to work, right? And again, if you're going to be scaling and rotating, you're going to have a lot of compute. So the whole point was this mechanism is very expensive, right? Now, we still want to deal with this as a classification problem. We all know what a classification problem is. Again, quick recap. You're given a bunch of features. You must determine what the category of the object is. And, we are going to be using binary classification to perform face detection. And specifically, we are going to be using an AdaBoost-based classifier. You will still have to scan because faces can be many sizes. They can be in many positions in the image. You still have to scan the image. You still have to check every possible size. And in spite of all of this, we must be able to do it really, really fast and really, really cheaply. Right? Otherwise, you're not going to get anything close to functional if you're trying to do this on your camera. So we're going to deal with this as a series of binary classification problems, and we're going to use AdaBoost. Now, AdaBoost uses a bunch of weak classifiers. So weak classifiers can be, what is the restriction on the weak classifier? Just has to be better than random. It shouldn't be perfect. That is a problem, because if a weak classifier becomes perfect, what happens to it? Can anybody tell me what happens when the weak classifier becomes perfect in this algorithm? Redundancy?
It will be enough to class.
Just trust the
No room for improvement.
The weight for that classifier becomes infinity. After that, you are blocked. There's nothing more you can do, right? And it's going to be infinite, but it was a perfect classifier on the training data. You have no bets on beyond the test data. So you have a situation where you want your weak classifiers to not be perfect, because most likely they're overfitting, right? What we found about AdaBoost is that it only overfits if your weak classifiers overfit. Otherwise, it doesn't quite, right? You can keep adding classifiers. It's a beautiful algorithm. And so we're going to use the weakest possible classifier. We're going to use decision stubs. And decision stubs are cheap, trivial, and take no effort at all to compute. And specifically, we use AdaBoost because this greedy mechanism in AdaBoost, as opposed to any other boosting mechanism, makes sure that you're getting the maximum bang for the buck and the smallest number of classifiers, right? So in the process, this also tells us what are good features. So this is a good thing. Now, here was the AdaBoost algorithm. Now, what were the steps in the algorithm? Anybody remember? You can look at the slides. So Hari, can you tell me what were the steps?
So the first step would be to assign equal weights to, and then the
Okay, let me ask somebody else the next step. Yunta, what was the next step?
I don't get your fault.
What was the next step in AdaBoost?
First, you have to initialize the distribution, and the next, you have to train the classifier that distribution.
And then Sagar, what was the next step? Find the minimum error. So that's part of finding the classifier, right? Okay, then what happened? So how do you update what weights? Are you updating only the weights of the misclassified instances, Aryan? You increase the weights of the misclassified instances and decrease the weights of the correctly classified instances. And specifically, what was the principle we used for that? What was the principle we used for that? Something to do with the accuracy of the classifier, yes.
So the incorrectly classified examples are like examples of hard instances. You want to be able to kind of motivate the system, like learn how to do those, but the easy ones are 2 examples.
And so, but how did we relate it to the accuracy of the classifier?
Yes.
A very accurate classifier. If they miss something, that's a very hard
If a very accurate classifier messes up, then whatever instances it misses are very hard to classify. So you want to increase their weights for subsequent classifiers to grab them, right? So can we raise this one? In the meantime, I'm going to, yeah. Just ignore the light over here. I'm not sure why we had this, but our idea was that if this was your error could go between 0 and 1. If the error was 0, then what was the weight of a misclassified instance? Infinity, because something that was perfect could not catch this. So you wanted this to be infinity. If the error was 1, what was the weight of a misclassified instance? Negative infinity error, the weight of a misclassified instance. How did you scale it? If the classifier is always, okay, sorry, if the error is 0.5, right? You're right. So if the error is 0.5, how much did we say what was the weight of a misclassified instance? 0, right? So the weight itself needed to follow this that we use. That's why I used epsilon 1 minus epsilon over epsilon. And we had a similar logic for the weight of the classifier. What was that? If the classifier was perfect, you wanted the weight to be infinity. If the classifier was random, you wanted it to be 0. And if the classifier was absolutely incorrect, you wanted it to be
I turned that off.
minus infinity, right? So we just based on these 3 simple principles, without looking at the slides, after you train your classifier, what was the next step? First, what was it? Can somebody say it aloud? So we wanted to first find out the error of the optimal classifier that we just learned, and then they updated the weight of the
data.
In what manner again?
Again, the misclassified ones, the weight increase. The correctly classified ones, the weight decrease.
And how did it relate to the classifier accuracy?
If the classifier was not misclassified, then it.
Okay, and what was the next step, Ishka? But before that, you had to assign a weight to the classifier itself, right? And how did you assign a weight to the classifier? If the error is 0, it's infinity. If the error is 1, it's minus infinity. If it's half, then it's a useless classifier. You give it no weight at all, right? And then finally, you had updated the weights of all of your instances, you renormalize them. So the whole thing kind of makes sense, right? Even without looking at these slides. Okay. And the final classifier was just a weighted sum of all the individual classifiers. The individual classifiers gave you a +1 or a -1, and the final classifier just did a weighted sum. So specifically in the example that I showed in class yesterday, we used just one kind of classifier. In the example, we used 2 features to represent the data, and the weak classifiers that we used were based on thresholds, right? You found a threshold value at which the best classification could be performed. You found the best feature to apply a threshold-based classifier, and thereafter you just perform the classification by comparing the feature value to a threshold. This is the cheapest classification you can perform. How many parameters does that classifier have? A threshold-based classifier, yeah. Just one, it's the threshold. There's actually 2. One is the identity of the feature. Which feature are you looking at, right? And the second is the threshold. So one is a numeric feature, the other is an index. And these 2 specify the classifier completely. And we want to use these classifiers because if you're looking at something like face detection, you want the compute to be very quick, right? And the final classifier, of course, was the weighted sum of the individual classifiers. If the weighted sum was positive, you said it's a face, otherwise it's not. And now our job is to train a classifier of this kind and to use it to scan the input image segment by segment, window by window, to find which windows there are faces in. And this computation, you're not worried so much about how much time it takes to train the thing, because obviously when you're using your phone, you're not training your model, right? When you deploy it, when it runs, it must be super fast, right? So again, I've chosen the Viola-Jones algorithm as an example to present over here, because we will see how we can actually work around many of the considerations that we run into in real life when we are performing, when we are dealing with classification and such like. So, and decision stumps we saw even in the last class, although they're just threshold-based classifiers, they can combine to give you, if you're using AdaBoost, they can combine to give you very complicated decision boundaries, like the one on the right, which has almost begun to approach some kind of a circle, right? Which is the correct decision boundary over here. So yeah. I have a second poll. Okay, this was easy. Someone on Zoom, can you answer both questions? First question, true or false?
False.
False.
False. Because why false? Why is it false? You're right that it's false. Why? You're not training the classifiers in parallel, right? Each one is building on the next one. What about the second one? True or false? Why? It is a meta classification method. That's the thing. Okay. And so boosting is the basis of one of the most popular methods for face detection, the Viola-Jones algorithm. Now, current methods use other classifiers like CNNs and SVMs. That's simply because compute has become cheaper, and we've managed to come up with efficient processors which can perform the more expensive computations that these algorithms require without consuming too much power and very fast. But the basic point is computation is not just time. Computation is power, right? If I'm going to be performing face detection on my camera, if I'm using an SVM-based classifier, I'm going to be able to do that on far fewer images than if I were using something based on the AdaBoost algorithm, because it takes so much lesser compute. Computing an inner product is expensive. Comparing something against a threshold takes no power at all, right? And so that remains one of the primary concerns when you deploy these things. And so OpenCV, which is one of the most popular libraries for computer vision, continues to have the Viola-Jones algorithm as one of its centerpieces, right? So the problem of face detection, how would we go about it? First, we want to define features. Should we be searching for noses, eyes, eyebrows? It's a good idea. It will probably work. That's how things were done in the past. It's very expensive. So expense is an issue, right? Then you can think of millions of features. Which feature do you use? That is also going to be expensive, right? And then the classification is combining evidence. How are you going to combine the evidence? That's the last bit. So I just said we're going to be using AdaBoost with decision stumps. What were the stumps being computed on? They were being computed on features. How are features typically computed? At the least, it's a projection on a basis. If it's a projection on a basis, that's an inner product. Inner products are expensive, not just in compute, but also power, right? So pretty much all of the standard approaches, if you get to more complex, fancy features, like is this an eye, is this a face, is this a nose, scanning for stuff, it gets more problematic, right? Much more expensive, much more power hungry. So our feature requirements, nonetheless, these feature requirements don't go away, right? You want the features to be sufficiently descriptive so that you can achieve good classification. but we want them to be extremely inexpensive to compute. You cannot afford to even compute an inner product for each detection, for each feature, right? So how can you compute a feature which takes less than an inner product? That's a challenge, right? And that's because you want phase detection to be running real time on cheap devices. And of course, power. Anytime you perform floating point operations, you're going to be sucking battery, right? If you're going to be doing phase detection in real time using something like a CNN, you better plug your phone into the wall socket, and then you can hear sucking sounds from the wall as you perform phase detection, because it's going to be drinking power, right? You want to be performing things in integer. Integer computes take no power, very much less power than floating point. All of these are practical requirements. And so given what we know about projections, computing inner products, bases, and the Wheeler-Jones algorithm, and the AdaBoost algorithm, how do we put all of these together to achieve all of these and still perform phase detection fast enough that you can do it real time on this clicker if I want to? So for this, first, what was a typical basis like? When I use a cosine basis, what did I need to do? Suppose I had a discrete cosine transform basis, and if I decided to use DCT bases as to extract features, what would I need to do to compute features? I got some image, I got the corresponding DCT basis. How do I compute that feature? What is the operation? Yeah, it was an inner product, right? You're projecting the image onto the basis. And what did this inner product operation comprise of? Lots of multiplies and accumulates. Is that cheap? Okay, now I'm giving you the choice. I can either use a discrete cosine time basis, DCT basis, or these checkerboard bases. Which one would you use? Checkerboard, why? Discrete. What am I doing? You're saying something? You did. Why would I use the checkerboard? Yes, Alex.
Because you're accumulating some.
It's just addition, right? Once I project things on checkerboards, everything is either multiplied by a +1 or a -1, which collapses to addition and subtraction. There is no multiplication, right? Additions and subtractions are way cheaper than multiplication. So the first thing we're going to do is to get rid of all of the more fancy features. We're not going to be performing KLT or principal component analysis. We're not going to be defining complex feature bases. We are not even going to be using discrete cosine transforms, although we know they're really, really good for representing images. We're going to back off all the way to these hard bases, which are just +1s and -1s, because you've reduced the operation of performing a projection to addition and subtraction, right? So, but then I'm using checkerboard patterns. Can I just use any odd checkerboard pattern? What was the difference between the first two lectures that we did on bases? The first one was a deterministic, right? What was the problem with deterministic bases?
Yes.
It was agnostic to the class of data, right? You would use the same bases for trees versus houses versus entire crowd pictures. It didn't know anything about the problem. What about the learned bases? What is the second kind of bases we used? Data specific. What was the specific one we learned? Eigenfaces, but basically the Cardinal transform of principal component analysis. What was special about that?
Fewer bases were able to capture most of them.
Fewer bases were able to capture. The bases are specific to the class. And we saw how phase bases were unable to explain a fishbowl, and this is the kind of behavior that we really want. So you want the basis representation to be specific to the class At the same time, you want something like checkerboards, which are class agnostic, right? Is there a golden medium between the two? Can I perform checkerboard-like operations to derive representations that are class specific? That is the key invention that these guys came up with. And that's where you have to twist your head around on your neck till you're looking backward and forward like an owl, because this was a very clever piece of arithmetic, right? You want to use checkerboards, but then you want to capture face-specific features. Suppose I give you this information. What kinds of features would you detect? What kind of bases would you come up with? Just edges?
Horizontal, vertical line.
Horizontal, vertical lines. Anything else? You guys, Ishka, any ideas? Folks back there, folks on Zoom, any ideas? What would you do? Lovely, right? So Vikram gets the idea. You want to still use these three bases, but then you want to make them localized in a manner that they're able to pick up on features of the face. So here's what we will do. We're going to use simple bases. They don't span the space. They are localized, as Vikram says, right? And they're not even very complicated. They're just like these 4 basic patterns that Viola and Jones described. One is just a little rectangle, which goes from 1 to 0, 1 to -1. The other is 1 - 1, 1 horizontally. You can have the vertical equivalent, -1, 1, and then 1 - 1, 1, and then you have the crosshash. So these are all just very localized bases, right? I can position them anywhere. Now this is beginning to look for local features. It's still using the same notion of checkerboard-like bases, except that you're trying to customize them to the class that you're looking for. Make sense, right? And so if I want to compute, for example, if I got this thing, if I wanted to place one of these things, these patches in horizontal form, then all I would need to do is, here's the image. I could put this right on top of my eyes, and it's going to give me a feature that tells me something about the presence or absence of an eye. I can take, for instance, the inverse of the negation of this, 0, 1, -1, 0, -1. And if I put it on the bridge of the nose, the feature is going to tell you whether the shape underneath looks like the bridge of a nose or not. Right? Make sense? Now the question is, what is the next question? If I tell you I can do this. Where do you place it, right? What do you look for? How many of these can you define? It's not very clear. The principle is those structures can be, the bases that we're looking at can capture such structures. But then now we're going to go back and look at the data to figure out where to place it and how to place it and what the sizes are, right? So the computation is, of course, trivial, because all you're saying is what is the difference in the average intensity of the image and the white and black regions. It's basically a differencing operation. You're summing all the points in this region, summing all the points in this region, and then subtracting, right? So how many computes does it need? If it's a k cross n feature, then how many computes does it need? Go ahead, tell me. K cross n, what? So are those multiplications or additions? Additions, right? So it's k times n additions as opposed to k times n multiplications, right? So you expect it to be much cheaper than multiplications. But if I'm running it on my phone, can I afford to do that 5,000 times? But can I afford to do it, right? So can I do this operation with fewer than k times n additions. So this actually goes to the next step, right? How would I do that? Squeeze them. So my claim is that with some preliminary processing, this can be done with only 6 operations, 6 additions, right? So this was Viola and Jones' brilliant insight. Okay, now I've given you the hint, and I'm telling you that there's some pre-processing going on. It's all integers, right? Can you tell me how I would do this? You're creative, think. Yes, Alex.
So essentially, if we just sum, we can take the difference and like let's pretend that it's whole.
Perfect, right? So here you go. Thank you. So here's what I'm going to do. So by the way, so these are what they were called the integral features. You have these little checkerboards, and they are the 4 basic patterns. They had their basic characteristics are length, width, the type. Is it this way? Is it plus minus? Is it minus plus minus? Is it plus minus plus? Is it a cross? And if it's a cross, what is the orientation? You know, these are the basic types, about 16 types, right? And so these 4 with different combinations. These are the only ones that Viola and Jones used. And to perform the computation using a small number of computes, here is the key trick that they used. And this is brilliant. You do one pass over the entire image. And so if I have an image, say I'm just going to write down the pixel values for example, just as illustration, and say I got say 1 0 1 1 0 1 0 0. Obviously, in your real picture, it's not going to be, you know, just ones and zeros, right? And then I'm going to compute what I call an integral image, where I make a copy of this 1 2 3 4 5 6. So 2 3 4 5 6 6. And at each position, I'm going to store the sum of all values at that location above and to the left. Right, so here the value would be 1. Here, if I'm looking at this position, above and to the left is just these 2, right? So the value is still going to be 1. Here, what would the value be? 2, right? What about this guy? 3. This. 3, 4. And what about here?
1.
Above and to the left. 2, right? This. 3. This. What is this? 4, right? What would that be? So if I'm at the 4th location, 1 2 3 4 5 6, right? 6. So you see what I'm doing, right? I'm summing everything at each point. I'm summing everything in the rectangle that ends at that point. This is a one-time operation, right? Done on the frame. So once it's done, I don't have to repeat the operation. This is my pre-processing step. That makes sense to everybody? The compute that we were performing? And so just to fill it up, right? This is going to be 3. This is going to be 5. This is going to be what? 7. You can just look at the ones above, right? This would probably be 10, right? And so on. You can fill up the whole thing. And so now this is so cool, because even the local computations, you're just going to be looking at the neighbors and you can and the current value, and you figure out what the thing is. So if you have an n cross n image, it's like 4 times n cross n times n. That's all the number of computes you're performing once, 4n squared. Now that you're done, so let's say I want to compute the sum of the values in this little rectangle. Just that little rectangle shown as D, right? What can I say? So if I'm trying to look at the sum of the values here, let's say this guy. If I'm looking at the sum of the values in this patch, how can I derive it from here using 4 computes. Actually, let me make it bigger just so, let's say I'm trying to look at the sum of the values in this entire region. Then how can I, so if I were to do it directly, I would need 8 additions, right? But then using this table, I claim I can do it using only 4. How can I do it using 4? So this one, 10 is the sum of everything, right? So 10 is the upper bound on the sum. Okay. But this guy here, 3, is the sum of everything above and to the left. So I must subtract 3, right? And then, of course, maybe I should stop it here just for illustration. So then out here, 3 is the sum of everything to the left. So I have to subtract that. But in the process, I subtracted this twice. So add that one back, right? And with 4 summations, 4 additions, I got the sum of the entire box, right? So pixel sum at 1 is the area of A. Pixel sum at 2 is the area of A and the area of B. Pixel sum at 3 is the area of A and the area of C. Pixel sum 4 is area A, B, C, and D. So if I want the area of D, it's pixel sum 4 minus pixel sum 3 minus pixel sum 2, but then I have to add back pixel sum 1 because it's been subtracted twice. Right? 4 operations, really trivial. And now, if I want to compute this integral over here, then it's the sum of the numbers in the white box minus the sum of the numbers in the yellow box. They also happen to share 2 corners. So in the worst case, I'm going to need 4 minus 4. That's 8 addition operations. I can do it more efficiently using just 6. Do you guys see how that happens? You're looking very puzzled. You're looking puzzled. You are puzzled? How? So did you understand how I could get this? Okay. So now if I'm trying to, my feature is looking for the sum of all of these values minus the sum of all of these values, correct? So that's going to be the sum of all of these values can be got from 4 additions. The sum of all of these values can be got from 4 more additions. Subtract, so that's 8 operations. And then 2 of those corners are shared. So you can actually, they're being reused. So if you get efficient in just 6 operations, you can compute the feature. So you're going to just need as many operations as the number of corners. And these are addition operations. Make sense to everybody? Yes, Ishka? Okay, thank you. How many of these features can I actually consider? Now, each of these checkerboards has a height and a width which is not known beforehand. As Ishka just pointed out, right? How wide are the eyes of a typical person? What is the variety of eyes we can find? How big is a person's nose? What is the variety in the size? We don't know. So each of these checkerboards can be positioned at each one of those position locations in the image, right? So if you have 8 kinds of checkerboards, and if each checkerboard can be, has 50 different size values, so 8 times 50 is 400, and then there are 1,000 different positions where you can place it. There are 400 different, 1,000 different features. I mean, the actual number of features ends up being, each feature can have many sizes, height from min to height max. At each size, it can have many number of starting locations, total number of checkerboards of one type, right? And so the actual, for any given type, is the number of sizes times the number of possible locations, multiply that by the number of checkerboard types. And the total sum ends up being in the hundreds of thousands of features, right? You're not going to be computing hundreds of thousands of features. We basically lost the whole point of the deal, right? So for efficiency's sake, even during training, they first, in the original paper, they actually zapped images down to 24 cross 24 pixels. They were performing face detection on these tiny 24 cross 24 pixel images, and they were getting it almost 100% right. It's amazing, right? Because that's how powerful the technique is. When you do that, it turns out that on images of that size, the number of possible features reduces to about 180,000. Then the sizes of these little checkerboard patterns, they restricted it to no more than 8 cross 8. And you can have other limits. You can say 4 pixels on a 24 cross 24 image. And so when you're done with all of these restrictions, these are just practical restrictions that you wouldn't worry about today because our computers are somewhat faster and processors are more energy efficient. But this is during training, okay? There are 5,000 or 50,000 possible features that you can come up with. And so the actual training is going to do this. It's going to have, you have a collection of face images, you have a collection of non-face images. For each of these, you're going to be computing all 180,000 features, right? But would we need all 180,000 features when you're performing AdaBoost? Some of you are saying no. Why no? Speak up. So weak classifiers are going to be selecting, each of the weak classifiers is going to be selecting one feature, right? So the actual number of features you will compute at inference time is going to be no more than the number of weak classifiers, right? So although during training, I may be investigating 180,000 features, once I've trained my model, I may find that I need a very small number of features, a couple of thousand, and that's all I'm actually going to ever have to compute. And so they're going to use the algorithm use AdaBoost with stumps. At each stage, we find the best feature to classify the data. And because the training data includes many examples of both faces and non-faces, we know exactly how to do this. The classification rule is a decision stump rule, which is just looking for a threshold. And the value of the threshold must also be determined. But this we already seen in the last class, no biggie, right? And so to train, you will collect a large number of facial images. Resize them all to 24 cross 24. That would be the face training set. You'd collect a much, much, much larger set of non-face images because not a face is a much bigger category than face, right? So you need a much larger training data set for not faces. And then using these, for each of these, you'd compute your 180,000 or whatever features and then just train an AdaBoost classifier. So during test, given any new image, you've already trained your classifier. You're going to just scan, okay? And the thing is, this whole procedure only scans 24 cross 24 images. And pictures are much, much larger, right? So you have to scan, and you can have multiple faces in an image, and they can be at different scales. So just the simple matching doesn't do it. We have to look for, we have to do something more. To detect multiple faces, you can, of course, scan, right? And then if you want to find faces at different scales, you can take your original image and scale it to different sizes and then scan. So all of that still works. The thing is, in spite of this being an AdaBoost-based classifier, in spite of everything else, it is not enough. We have to play more tricks. And before that, I'll let you take this poll. Okay, you're probably wondering about the answers. Only the first statement is true, right? Bases like checkerboards can be computed efficiently, which enables real-time face detection. The Bueller-Jones algorithm, as I said, is still in OpenCV. As we just saw, they are able to represent facial features if correctly positioned and scaled. And the fact is, these checkerboard patterns do just fine, right? It's just so you're good. Now, here's the problem, right? What is the actual classifier we are using? The actual classifier looks like so. I have a whole bunch of weak learners. All of these are threshold-based learners, right? So I have H1, H2, and so on. All of these are threshold-based learners. And my score is summation I, alpha I, hi of x. Now, what was the rule I was using to decide if it was a face or not? What was the rule I was using? I was looking at the sign, correct? So this was because H is either +1 or -1, alphas are all, So if I just take this sum, if the sum is positive, it's a phase. If the sum is negative, it's not a phase. But then I can make different kinds of mistakes. I can call faces non-faces, right? I can call non-faces faces. Suppose I want to be conservative. And I want to say that when I call something a face, I want to be certain that it's a face, or more certain that it's a face. Then our current rule is S greater than 0, right? That is the rule that we used to decide if it's a face or not a face. How would I modify it to ensure that when I call something a face, I'm more certain that it's a face? Increase the threshold, right? I can say S greater than some theta, where theta is greater than 0. And that way, I'll be rejecting some things that are faces, but you're going out where you have much greater certainty that things are faces. Similarly, if I want to say that when I reject something, I want to make sure that it's not a face, but I never want to reject a face. What would I do? So S greater, so if theta greater than 0, fewer false acceptances, right? And if theta is less than 0, fewer false rejections. That makes sense? So I can just still use the same classifier that I've got, and I can tweak it without actually doing anything more to decide to be more conservative or less conservative, right? So here I'm calling this Y. I can just change my threshold, and by changing the threshold, I can decide whether I'm accepting more faces or whether I'm rejecting, I'm being more conservative in accepting faces. So what will happen is that you're going to get what is called a receiver operating characteristic. The classifier is going to give you a score, and for any score, there's a false rejection rate. False rejection rate is what fraction of faces are being rejected as being not faces. You want that to be 0, right? There's a false acceptance rate. What fraction of things that are being called faces are not faces, right? So when you reject something, what fraction of the things rejected are faces? That should be 0. It was rejected, but it was a face. Similarly, you accepted it, but it was not a face. That's false acceptance, right? You want that also to be 0. So at any threshold, you're going to get some trade-off between false acceptance and false rejection. And as you modify your threshold, if you plot the performance, you're going to get a curve of this kind, the receiver operating characteristic, which tells you how false acceptances are traded off with false rejections when you modify your threshold. And so you can actually plot these And based on this plot, you can decide where you want your threshold to be so that you don't reject a face, never reject a face or never accept a false face, depending on what your choice is. Now, going back to the original Vialo-Jones algorithm, it turns out that this technique that we just discussed, it's efficient, it works fast, but not fast enough. It's also not accurate enough. So now here you have a classifier. So this is where, again, we get into some clever tricks, things that are worth thinking about and that you can carry, lessons that you can carry to other places, right? We're already using an AdaBoost classifier, which is combining weak learners to making it stronger. And we expect it to perform really well, but it turns out that it's not really doing a great job. So I have a practical application where I'm trying to detect faces. How can I improve it? So here's what these guys did. They made a cascade of classifiers. Now, each classifier rejects some things and accepts some things as faces, potentially faces. And now each of these classifiers is set such that the threshold is set to be negative, such that when the classifier says it's not a face, then that's almost certainly not a face. And so the data that the next classifier sees has a higher density of faces. Then the next classifier is going to be optimized for the reduced set of data. And on that, once again, you can set a negative threshold. And so when that second classifier rejects something, it locally is also almost certain that it's not a face. And so whatever it passes through, it doesn't mean that it's never going to accept a non-face. It's just that when it rejects something, it's definitely not a face, right? So then what the second classifier passes through is going to have a still higher density of faces. I can keep cascading these classifiers, right? And so you end up with a cascade of classifiers. Now, the way it happens is that during training, this must be taken into, this training also becomes a greedy process. So you train your classifier one, you get your training data, and you train C1. Then you check your C1, and based on the receiver operating characteristics, you decide your threshold. And so now you've chosen your threshold Y over here, such that when you use this threshold, everything you reject is definitely not a face from your training data, right? So then you pass all of your training data through this classifier. You're going to get this TRN prime, which is the same as this training data with these data gone, right? That's a reduced set of training set. And then on this guy, you train your second classifier. And then after having inspected the second classifier, you choose its own threshold so that whatever comes out, so that faces are never rejected, right? And then you have TRN double prime. You pass your entire training data through this chain of two classifiers. And then you train a new classifier on this more positive, dense data and keep repeating this process. So you end up with a cascade of classifiers of this kind. And this is going to be, and during inference time, when you're looking at any particular window, it must pass through the entire chain of classifiers for it to be tagged as a face, right? And yeah.
It makes sense to essentially bring that threshold.
So again, because you're getting a new classifier, we don't know whether the threshold will actually increase, right? The second classifier is entirely different from the first classifier. It might be working on different features, right? And so that's how it works. And if you actually look at the kinds of features that the classifier ends up finding to be useful across all of the classifiers, they end up actually looking like these features. The first one detects eyes. The second feature detects the bridge of a nose. These are automatically derived. And so here we have a perfect combination of checkerboard-based bases and data-driven bases, right? Where I actually get the simplicity of computation of a checkerboard of standard bases, like we could have done a DCT for all you care, right? But it has been designed to be localized and select class-specific features by the algorithm itself. So we see how the representations, you got this intermediate representation that was neither purely data-driven nor purely deterministic, right? And the cascade of classifiers, of course, works like so. Yes.
Is also effective in detecting classes which have round edges.
This has nothing to do with faces have round edges. Right? Look at everybody's face over here. How many people have a square face? Outside of SpongeBob and SquarePants, I haven't seen anybody with a square face. Yes, yes, I know.
Each classifier has those 6 features which we are using.
They're the 6 patterns, but then if you can scale it, right? And then you can invert the colors. So you have all kinds of scales, all kinds of inversions. So all of these are combinations, and you're searching them for the appropriate one. Yeah.
So I think this, the quiz at this link is from last week.
Oh, I copied the wrong one. Okay, sorry. Ignore it, right? Sorry. So on real images, again, going back, they worked on 24x24 sub-windows. Again, when these guys trained their first system, they killed my cluster. Yes? No, they're all, because once you angle it, our ability to just compute it using 4 additions goes away. Right? It has to be axis aligned.
So images which have certain interface won't be identified.
Yeah. No, because the boards are themselves. I mean, you may end up getting a bigger feature, right? Because you have these cross-hash picture checkerboards, and so those will capture angular patterns. Right? Yeah.
Each classifier is also an AdaBoost classifier.
All of them are AdaBoost classifiers, because you're restricted to using thresholds, and you're restricted to using these very simple features, right? And so here, in their original work, they were scaling the detector rather than the images, because instead of if you've trained your features, then you can scale all the features down by 0.75, right? And now you're going to be detecting faces and the thresholds, and you're going to be detecting faces which are 75% of the size of the original, and so on. Yeah. Yes, Alex.
We said that Viola Jones, but the original Viola Jones, without like these extra things we're doing, it had an issue of not being as fast as we would like. So the cascading method seems to introduce even more computation. Actually,
no. So it turns out because each of the subclassifiers. So if you look at any particular window, I may have 3,000, any particular image, I may have 30,000 windows to analyze, right? Or depending on whatever. The classifiers are good at rejection, and each of them is simple. So they're going to have maybe a section of 31-week learners, at 30-week. So you're going to get rid of the easy ones before passing them on to the next classifier.
Like subclass cascading, so it's smaller than like the original Viola Jones.
So it's smaller than a really large classifier. You can always increase the Viola Jones classifier to be very large, and then it would be accurate, but then it's not going to be efficient, right? So you trade it off for saying, I'm going to be rejecting things I really don't need. And then as you go deeper down the chain, each classifier is getting fewer and fewer things to analyze. And so the actual computation becomes very cheap, right? And for scanning, of course, you could be scanning with any kind of shift 1 pixel or 2. And what will happen is that if you detect a face here, if you shift things by a pixel, you're still going to see a face, right? So then there's some additional heuristics where you merge adjacent things around and so on. But that's the engineering side of things. There are several concepts in the whole process of seeing how this face detector was built, which come across. One was, what is the key concept we wanted to point out? Besides AdaBoost? Bases that are neither data-driven nor deterministic, right? You can design those. So AdaBoost was, a very nice classifier, but yes,
We had like four primary features like
Yeah.
this one. So for the first one, we just use integral sum to calculate those things. So what if we had like -1, what minus?
it doesn't matter. For each rectangle, you're going to use an integral sum. So depending on the number of rectangles, you only have 4 operations. That's it. Right? Okay. And so here in their paper, these were the faces and these were the face images that they had for the training. These are all 24 cross 24. And I recognize many of these guys because they're friends from MIT. Yeah.
We could use the -1, 1, 1, -1 feature. I think if we could use integral sum, we could also take slanted or tilted images. This would be just basically
Many blocks.
okay.
So because if you wanted to make something, if you wanted something of this kind, then you're probably going to build. You just made the computation more expensive. That's it, right? You're keeping it simple. And so here are some examples that they had. There's a Judy Batts image. See how they get faces at many scales. This is from some conference, if I'm right. I don't remember. But you can see all of those faces. They got pretty much every face. That's this famous Seinfeld one. Some of these, the soccer team, I don't remember which one. That one, I think, has some of my friends. It missed one of those faces. Basically, if you're wearing a sherwani, it doesn't like you. Right? And so that's one in the middle is from Star Trek. That missed one face, right?
Soccer ball is a face.
Yeah.
There was a soccer ball that was a face.
Of course, it's a face. Doesn't it look like a face to you? You're supposed to say, yes, I'm the prof. I own your grade.
Yes.
Yes. No question? Anyways. So these guys, they were horrible coders. They were brilliant scientists. And so I hated them for a long time because I set up a cluster, as I said, which was meant to be for the entire lab, but sneakily it was meant only for me. And then I got kicked off for six weeks or 3 months at a time. And they were training on only 15,000 faces. It doesn't even begin to make sense. I'd look at their training data and say, guys, why are you using 500 processors for 3 months? But that's what they did. And then we got a software engineer who made it work on 2 computers in a day. So, I know, but their final detector had 38 layers in the cascade, 6,060 features, which means that of the 180,000 features, right? Potential features, they're only using 6,060 across the entire cascade. And moreover, most of those features are not even going to be computed because they're later in the cascade. And so the maximum number of amount of computation that you're going to do in one segment is 24,000 additions. So for 24,000 additions, which is nothing, 24,000 additions is basically 24K additions, absolutely nothing, right? 24,000 flops, not even a proper flop. It's integer operation, right? You classify a block. And so in 2003, on a 700 megahertz processor, they were doing this at 15 frames per second, a pretty big picture, a 384 cross 288 image. But I know that even in 2000, they were giving us live demos as we walked into labs and such like, right? It was very efficient. It was a game changer. Basically changed the world. Computer vision was never the same again once these two guys came out with this algorithm. But it wasn't just computer vision because they introduced a whole bunch of new concepts in the process, which basically showed us how you can combine different mechanisms for deriving features, how you can use the simplest possible technique for classification and still build very complicated things. AdaBoost was a very nice idea. The authors, so your friend who actually came up with it, used to work with these guys on some of this work. And nobody really found a compelling use for it till this came up. And then afterwards, it became a very big thing, right? So here's one where foreground versus background segmentation. And again, you got to worry about how your training data is set up and so on. You want to worry about, what kind of window sizes that you get. The same window size can miss one guy over here. Same feature size can miss one guy in there and get the next one. So you get all of these relatively minor issues that you would worry about. And these are things that are specific to this kind of representation. They wouldn't appear if you're using, generic DCT-based representation or a PCA-based representation. Anytime you're coming up with these hybrid schemes, you will deal with these specifics, right? What is the size of the patch and so on. Anyway, so I'll just stop here. 1 minute early, actually 15 minutes early because we spent time fiddling with the project. This class was meant to be light. It was meant to begin and early. It didn't because, thank you, Adnan. Right? But again, there were lessons learned. And the lessons we've learned are eigenface features. These were just the hard features, cascaded strong classifiers. These are the lessons that people will typically give you when they're talking about boosting. But we learned something else, something very important. That representations can be customized. And there's actually a continuum of representations between fully deterministic and fully data-driven. And where you want to live can be based on many factors, including computation, what you want to represent, and so on. And every one of those has a job somewhere. They're all employed. Thank you.